The question for today is design tic-tac-toe game. For those of you who do not know what is a tic-tac-toe game, let's very quickly go through this. It is a two-player game where each player is assigned a sign. So let's say in our case player 1 is assigned X and the player 2 is assigned circle. It is played turn by turn, and in each turn, so this is also played on an n cross n matrix. So it can be of 3 cross 3, 4 cross 4 or 100 cross 100. And during each turn, player places his sign in any of the cells. So the objective of this game is that player needs either the full row with his signs or the full column, any of the full column. So you can take like either this, if it is filled with x's. So if we had a scenario like this, the player 1 will win because he has the full row, or the full column, any of the columns. So like this, any of the columns. So in this case, player 2 is the winner. And also we have two diagonals. So very quickly just draw this. Or the other diagonal. So this is basically what the game is. Now in our question, what we have is the size of the tic-tac-toe is first initialized. So in this case it is initialized by 3, and then a move method is called. So move method has the first argument as the first param as the row, then we have the column. So this indicates in which cell a player is making his move. According to this question, it is guaranteed that it will be a valid empty block. So let's say the size of an array is 3. It will never be like the row cannot be row 4 column 4, and it will always make sure that the cell is empty. Let's say player himself or the other player has not already taken a turn on that particular cell. So coming back to this example again, in this example the third param is the player ID. So in this, player 1 makes a move at 0 0 position. So we put an X at this position. In the next, player 2 takes a turn at this position, which is 0 row and column 2. So we put an 0 at this position, and likewise this continues. And if we quickly come to this point where player 1 makes a move at this position, which is this, we need to return that player 1 has won, because in this we have the full row which has the same sign. Otherwise we need to keep returning 0, because till this point nobody is the winner. So I hope the question is clear. Now I think we'll start with how we can approach this question. Let's discuss how we can approach this problem statement. What we can do is, at each point this move method is called. So let's take this as an example, 0 0 player 1. Now at this point I make a move at this position. So whenever I make a move at this position, I know that if with this move I am winning the game, then either it is possible either because this row, which is row 0, has all x's, or this column 0 has all x. And what other possibility can be that if in case I am in a diagonal position, and the I mean, if this row call is a valid diagonal position, then I can check the whole diagonal whether it has all x's. Check diagonal. Whenever this condition meets, I can return 1, and in case, like, let's say I have an empty or other sign, let's say circle here, I can just come out of this, I can come out of the check, and I don't need to go down and check for any further cells. One interesting point here is that how will I know whether this is a valid diagonal cell? So let's quickly derive the formula for a valid diagonal cell. So in this example, what constitutes a diagonal? So it is 0, 0, it is 1, 1, 2, 2. So this comes out to be row equal to col. So this is one formula. So whenever we know that a row is equal to column, we know that this is the diagonal. Now we can also have another diagonal, which is this one. So let's just quickly write and figure out what is the formula for this. So it is 2, 0, 1, 1, and 0, 2. So this looks like it is row plus col equal to n minus 1. If you want, like, we can also discuss whether, I mean, any other, if you see, like, when I thought of this formula, I what I did was I also checked whether, like, I was not sure whether this is true, and if any other cell in, like, is this cell, this cell, this cell. I just quickly checked the sum of what is the sum of these cells. So if I take this as an example, it will be 2, 1, which means it is 3. So it seems like my condition is correct. Now, in terms, if I have to code this out, it doesn't seem like very complex. All I need to do is I need to iterate the row. I know the size of the array, so I need to do n iterations in the row, n iterations in the column, and if it's a valid diagonal, then I know the formula for diagonal and need to, like, in this condition, I'll initialize my row with 0, column with 0, and after each iteration I'll do +1, +1. In the other case, the other diagonal, I'll initialize my row with n minus 1, column with 0, and I'll keep decrementing row and incrementing my column value. So it is a fairly straightforward comparison, but let's talk of the space and time complexities. So in terms of space complexity, it is O of n square. It is very evident that we'll have to keep a matrix, and we'll have to keep storing, like, whether a particular cell has a x or a circle. So that is why the space complexity becomes O of n square. Now let's quickly talk about time complexity. In this case, whenever a move method is called, what we are doing is we are doing n iterations for the rows, and we are doing O of n iterations for column plus O of n iterations if it's a diagonal, and at, like, if it's the center point, in that case it is possible that we'll be doing two iterations for, because it's the condition for diagonal will meet for both diagonals, so it can be O of n in the worst case, but usually more often than not we'll have two O n iterations, and in the worst case we'll be doing n iterations, but mostly will be as soon as we'll meet a negative condition, we'll come out of this check. So like To few this might seem like O(n) square complexity. So let me just quickly give a relevant example and explain why it is not O of n square. So in this case, like in if you consider a 3 cross 3 matrix, we are more or less doing 3 plus 3 plus 3 plus 3, which is like more than, which is like 12 comparisons, and O of n square is 9. But consider the number as, let's say, n is equal to 100. So in this case, in the worst case, what we'll be doing is we'll be doing 100 plus 100 plus 100 plus 100, which is 400. Now, but if you consider 100 square, it comes out to be 10,000. So for those who have a confusion whether this is like O(n) square complexity, it is actually not O(n) square complexity, it is O(n) complexity. It is basically 4 O(n) complexity, which is considered to be O(n) only, and I've given a relevant example which shows why this is relevant. Now if you look at it, I do see that we can somehow improve the time complexity. So what we are actually doing here is that each time we are checking, what we are looking at is we are looking for, so when I'm iterating this row, what I'm looking for is I'm looking whether my row 1 has x equal to 3 or not, or this row has x 3 times in this row. Similarly for column. So what if I can use some extra space, and just keep maintaining this count. So let's take this example and walk through this. So I make a move here, so I can say row 1, player 1 has count 1, then player 2 does a move here, so I can say row 1, player 2 also has count 1, then I can say it's now equal to 2. So this is how, if I keep maintaining the count, and as soon as take a scenario where I have column 1, player 1 equal to 3, player 2 equal to 0. As soon as I make a move here, let's suppose this was 2 earlier, I make a move at this position, I'll do a +1, it will become 3, and as soon as it becomes 3, it becomes equal to n, and this tells me that player 1 is the winner. So this reduces the time, it also reduces the space complexity, because here again we are using constant space. What we are doing is we can have like we have n rows, n columns, and we have similarly 2 diagonals, diagonal 1 and diagonal 2. This is the amount of space that we'll be using. So code this up. So for each player, we need to remember number of times we have encountered its sign in any particular row, any particular column, or we have the 2 diagonals. So what we can do is, let's say we have a let's say we have a 3 cross 3 matrix. So what we can do is, for player 1 we can keep an array of size 3 where each index is representing that particular row. Similarly we'll have this again for player 2. So in this each index in the columns is indicating each particular column. So let's quickly walk over this through an example. Let's say player 1 does a move at 0 0. 0 0 is this position, it is x. Now what we need to do is we need to go at 0th index and do a +1 here. So it was initialized with 0, all of this. Alright. So to code this up, as we had discussed, we'll need to remember number of times we have seen the symbol of player 1 or player 2. So to remember this, we can have a simple data structure of an array. So for a n cross n or 3 cross 3 size matrix, we can have an array of size 3 where each index will represent that particular row. So 0 index represents this row, 1 index represents this row, and second index represents this row. Similarly for columns. And then we have our diagonals. So diagonals is not an array. We can have simply two diagonals. So player 1 diagonal 1 and player 1 diagonal 2. Similarly, we'll have the counters here for player 2 and for both for player 2 also. So let's go over this using an example and it will become much more clear. So the first move was at 0 0. So we'll create x here, and what we need to do is we need to increment the value of 0 row from 0 by 1. So we do 1 here. Since it was column 0 again, so we'll do +1 here again. And now we have a condition for diagonal, which is row is equal to column. So since 0 0 is meeting that condition, so we'll do +1 here as well. It was actually 0 at the start. Now the next move is at 0 1, which is this position. So again we'll go here. So this is 0 row, so we'll do +1 here. So again 0 0. Then it is column 1. So column 1 is this position. So we'll do +1 again here. And it does not meet any diagonal condition, so we'll move ahead. Now the user player 1 again makes a move at this position. So this is row 1. So row 1 we'll do +1 here, and then it is column 0. So again, so it was 1 already, so we'll make it 2. As soon as we make it 2, we'll check whether is the value equal to 3. In case the value becomes equal to 3, we can exit we have found the answer. But since this is 2, we'll keep going. Now this position is not a valid any diagonal condition, so we'll continue. Now the player 1 does a move at 1, player 2 does a move at 1 1, which is this position. Now so again here it is row 1, so it will become 1, and it is column 1. So it was already 1, we'll make it 2. Now this also satisfies the condition of diagonal 1 as well as diagonal 2, so we'll make it as 1 and 1. Now player 1 again makes a move here, which is 2 0. So for row 2, we'll again make an entry of +1. And for column 0, it was 2 already, so we'll make it 3. As soon as we make it 3, we'll also check whether the column that we modified or incremented now has the value player 1 column equal to, if player 1 column equal to n. And if this is true, then we have found the answer. So let's quickly code this up. Before that, there's also, if you check this you can also do one optimization. Now instead of keeping two separate rows for player 1 and player 2, if we decide that for player 1 we'll do +1, and for player 2 we decide if we do -1. So what we can do is we can have single rows, single columns. So in this condition again, my values would be modified like this. Let's quickly walk through this with this. I'm not taking diagonal diagonal in the example because I just want to explain the concept of using +1 and -1. So the idea is that as soon as whenever we want to make a comparison, we will check the absolute value. So if let's say the whole complete the complete column is with 0 0, so the value would be -3 and if you check the absolute value of 3, it will be equal to n, and then it will give us the result. So just to quickly walk through this example, in 0 0 we are at this position. We're at this position, we'll do +1 here. It was 0 0 initially, so we'll do 1 +1 here and +1 here. In the next move it is 0 1, so and it is for player 2, so we need to do a -1. So for row 0 it was 1, so we'll do a -1, it will again become 0, and for column 1 it was 0, so it will become -1. Now the next move is at 1 0, so for row 1 it was 0 earlier, it will become 1, and for column 0 it will become 2. Then we have a move at 1 1, so here again at row 1 I'll do a -1 because, and at column 1 I'll again do a -1, so it will become -2. Now the next move is at 2 0, so this will become 1 and column 0 will become 3. Now I'll just compare absolute value of rows 2, and if this is true, this is my answer. Quickly let's go over the code. As we had discussed, we'll have a list of rows which will be of size n. Each index is representing that row number, and similarly we'll have a list of an array of columns here also of size n. Then we have diagonal 1 and diagonal 2, and then we had discussed that what we'll do is for player 1 we'll do +1, and for player 2 we'll do a -1, and then use the absolute value to check if the current value is equal to n. So let's quickly walk through. So for example, we had 0 0 1. In this case we know the row is 0, so what we'll do is we'll go to first we'll from this player val hash map we'll get the value. So in this case we'll get val equal to 1. Now we have row equal to 0 for this input, and then what we do is simply add the value. So self.rows will become 1 0 0. In this case, as soon as we do an addition, what we'll do is we'll check if my value is equal to the size of n. If it is equal, that means we need to return the player. Similar thing is being done for columns as well. So for column 0 we'll have something like cols equal to 1 0 0 after addition, and again we'll check the value. If it's equal to the size of n, we'll return, and we know that he's the winner. So for clarification, let's do for player 2. So in this case he has added in cell 01, which is row 0, so this value will come 0. Again we'll check whether the absolute value is equal to 3. In this case, since n is equal to 3, it's not. Then we go ahead, we'll do calls column 1. Column 1 was not there, so we'll do -1 since value is -1, and again compare the absolute value. If you look below, this is the diagonals condition. The first condition is column and row should be of the same value, and then we increment or decrement, basically updating the diagonal value with val +1 or -1. Similarly, for the other diagonal, we had already discussed the formula that column plus row value should be equal to n-1. So overall, this is the very basic solution. I have also added the code in the description below, so for those they can check the description and use that code. So if we very quickly talk about the time and space complexity, we can say that it is of constant time, since we are doing four operations each time. Here, so we are doing constant operations, so it can be said to be O1. Each move function is, and if you talk about space complexity, we can say, since we are saving a list of rows and list of columns, so we can say that it will be O of n.